We start with this chapter to learn about architectural acoustics. The basic purpose is to prevent potential acoustic problems that may occur in architectural design. The intermediate purpose is to use architectural acoustics to create a comfortable acoustic environment for building users. And the advanced purpose is to design concert halls. The basic knowledge of architectural acoustics mainly includes people's recognition of sound, the physical characteristics of sound waves, and the physical phenomena generated in the process of propagation, and the subjective characteristics of people's hearing. The basic properties of sound mainly include the generation and propagation of sound, frequency, wavelength, and speed of sound, frequency band, diffraction, reflection, scattering and refraction of sound waves, transmission and absorption of sound waves, wave interference and standing waves. Sound originates from a vibrating object, and a vibrating object that radiates sound is the source of the sound. Sound waves are propagated outward by the vibration of the particles of the medium. Since the vibration direction of the particle is parallel to the propagation direction of the sound wave, the sound wave is a longitudinal wave. The time it takes for a sound source to complete one vibration is called the period. The number of vibrations in 1 second is called the frequency, and the frequency is the inverse of the period. The distance between two adjacent in-phase particles on the propagation path of a sound wave is called wavelength. The speed of sound waves in an elastic medium is called the speed of sound. The speed of sound is not the speed of particle vibration, but the speed of vibration state propagation. The magnitude has nothing to do with the characteristics of vibration, but is related to the elasticity, density, and temperature of the medium. The sound speed calculation formula reflects the relationship between the sound speed in the air and the air temperature. It can be seen that the sound speed increases with the increase of the temperature. The relationship between sound speed, wavelength, and frequency is C is equal to F lambda. Since the speed of sound in a certain medium is determined, the higher the frequency, the shorter the wavelength. This table gives the frequency range of sound waves. Among them, the frequency range that the human ear can hear is between 20 and 20,000 Hz. The sound wave below 20 Hz is infrasound, and the sound wave above 20,000 Hz is ultrasonic. Neither infrasound nor ultrasonic can be heard by humans. The frequency range considered for architectural acoustics is between 100 and 4,000 Hz, and the corresponding wavelength range is between 3.4 to 8.5 cm. To reduce the workload of acoustic measurements, the frequency range is divided into segments. Sound waves propagate in a certain direction in the same medium, and sound rays are used to represent the path of sound waves. At a certain moment, the envelope of the points reached by the wave is called the wavefront. In an isotropic medium, the sound ray is a straight line perpendicular to the wavefront. If the wavefront is flat, it is called a plane wave, and if the wavefront is spherical, it is called a spherical wave. The sound ray of a plane wave is a parallel line perpendicular to the wavefront, and the sound ray of a spherical wave is a radial ray centered on the sound source. The sound wave radiated by the point sound source is a spherical wave, but it can also be approximated as a plane wave in a local range far enough from the sound source. Matrix-arranged point sound source can also be approximated as plane waves when the sound waves emitted have the same phase. According to Huygens principle, a new wavefront can be obtained. The Huygens principle states that at any moment, every point on the wavefront can be regarded as a new wave source that emits wavelets. At the next moment, the envelope of this wavelet is the new wavefront of the actual wave source at this moment. As can be seen from the figure, point O is a point sound source. the wavefront at time t is S1, and the radius of the wavefront is the product of sound speed and time. The new wavefront at time t plus 30 is S2, and the radius of the wavefront is product of the speed of sound and time t plus 30. When the sound wave encounters the baffle in the propagation path, it no longer propagates in a straight line, but continues to propagate behind the baffle in a new propagation direction. This phenomenon is called diffraction. Finger A shows that the play wave encounters a baffle with a small hole, and the diameter of the small hole is much smaller than the wavelength. When the play wave propagates to the baffle, it can pass through the small hole. This is equivalent to a new point sound source, and continues to propagate as a spherical wave. This has nothing to do with the random play waveform. Finger B shows that the play wave encounters a baffle with a large hole. The size of the hole is much larger than the wavelength. This is equivalent to the propagation of spherical waves by several new point sound sources. Therefore, the shape of the newly formed envelope is more complicated. Finger C shows the diffraction of play waves at the end of the baffle. When the size of the baffle is much larger than the wavelength, the wavefront at the end of the baffle is bent, and the acoustic saddle area is formed behind the baffle. Finger D is the same as finger C, and it also shows the diffraction of sound waves at the end of the baffle. However, the sound source is a spherical wave, and the size of the baffle is smaller than the wavelength. It can be seen from the finger that the wavefront has almost no affected. There is no sound source area behind the baffle. When the sound wave encounters a baffle with a size much larger than the wavelength during the propagation process, the sound wave reflection phenomena will occur. The reflected wave has the same waveform as the incident wave. The solid line in the finger represents the incident wave, and the dotted line represents the reflected wave. The reflected wave is like a mirror image of the sound source point O, with the versal sound source point O prime. Point O and point O prime are symmetrical to the reflection plane. At the same time, the wavefront radius of the incident and reflected waves are equal. The basic content of the law of reflection is 1. The normal of the reflective surface is on the same plane as the incident ray and the reflective line. 2. The incident ray and the reflected ray are on both sides of the normal. 3. The angle of incidence is equal to the angle of reflection. When the oscillating size of the obstacles encountered by the sound wave during propagation is close to or smaller than the wavelength, the sound energy will be scattered into space, resulting in scattering rather than directional reflection. When the conditions of the medium change or the temperature in the same medium change, the speed of sound changes, resulting in a change in the direction of sound wave propagation. This change in the direction of sound propagation caused by the speed of sound is called reflection. When the vertical temperature gradient is large, the sound wave will bend towards the low temperature due to the large sound speed in the high temperature air. Finger A shows that the air temperature near the outdoor ground is higher than that of the upper part during the day. Since the sound wave moves upward away from the listener, a sound saddle area is generated and the propagation distance is shortened. Finger B shows that the air temperature near the ground is lower than the upper part at night or early in the morning. Since the sound waves are downward and reflected, the sound waves travel far. Sound waves are also bent in a similar way with the wind. Downwind propagation can travel farther than headwind propagation. Headwind propagation not only does not travel far, but also creates a sound saddle area. According to the law of conservation of energy, the total sound energy incident on the component in unit time is equal to the sum of reflected sound energy, absorbed sound energy, and transmitted sound energy. The ratio of the transmitted sound energy to the incident sound energy is transmission coefficient, and the ratio of the reflected sound energy to the incident sound energy is reflection coefficient. A material with a small transmission coefficient is a short insulating material. Materials with a small reflection coefficient are short absorbing materials. When the short absorbing material is attached to the partition wall, the short absorption coefficient is equal to 1 minus the reflection coefficient, which is equal to the ratio of the sum of the absorbed short energy and the transmitted short energy to the total short energy. When the short absorbing material is placed in the room, alpha is equal to 1 minus gamma and tau, which is equal to the ratio of the absorbed short energy to the total short energy. When two waves propagate in the same medium, after intersecting in a certain area, they still maintain their original characteristics and continue to propagate without being affected by another wave. But the particle in the intersecting area participates in the vibration of the two waves at the same time, and the vibration of the particle is the combined vibration of the two waves. This is the principle of superposition of waves. According to the principle of superposition of waves, when the waves from two wave sources with the same frequency and phase meet and superimpose, the vibrations in some positions always strengthen each other, while the vibrations in other positions always weaken or cancel each other. This phenomenon is called interference of waves. Point O in the interferogram is a wave source, which emits spherical waves and reaches points O1 and O2 at the same time. According to the Huygens principle mentioned above, O1 and O2 can be regarded as two new wave sources with the same properties, and the emitted waves have the same characteristics such as amplitude and wavelength. When the path difference between the two new wave sources to point A is equal to 0, or an even multiple of the half wavelength, the phase of the two waves are the same, the combined vibration is the strongest, and the amplitude is the largest. When the path difference between the two new wave sources to point B is equal to 0, or an odd multiple of half wavelength, the phase of the two waves are opposite, and the combined vibration is the weakest. When two identical waves travel in opposite directions on the same straight line, the waves produced by superposition are called standing waves. This picture shows a standing wave formed by the superposition of the incident wave and the reflected wave when a plane wave is perpendicular to the total reflection wall at a certain moment. The reflected wave can be regarded as a wave simultaneously emitted from the virtual short source, and the incident wave is always symmetrical about the reflecting plane. Therefore, at a distance L from the reflective surface, the superposition of the incident wave and the reflected wave is equal to the superposition of the short pressure at 2 points of the same wave at a distance of 2L. In the same wave, the instantaneous short pressures of 2 points separated by an even multiple of half wavelengths are equal in magnitude and have the same sign. The maximum short pressure at the superposition is 2 times that of its individual wave. The place where the short pressure is greatest is called the antinode. In the same wave, the instantaneous short pressures of 2 points separated by an odd multiple of half wavelengths are equal in magnitude and opposite in sign. The short pressure and amplitude at the superposition are always 0. The place where the short pressure is the smallest are called nodes. When a standing wave occurs, the waveform does not propagate, and the positions of the antinodes and the nodes are always the same. Hence, it is called a standing wave. The antinode is on the total reflection surface. The node and the antinode are adjacent. The distance between the node and the antinode is a quantum of the wavelength, and the distance between two adjacent antinodes is 1/2 of the wavelength. Therefore, the conditions for a standing wave to be generated between two parallel walls separated by L and the antinodes to be located on the surface of two walls are L equals n times half wavelength, and n is a positive integer. Frequency can also be expressed. Think about it. How are these fundamental properties of salt views used in architectural acoustics design? As the old saying goes, the world has ears, echoes in the empty valleys. Before you see the face, you hear the sound first. What kind of sound view properties do these ancient sayings describe? What are some ancient buildings that took advantage of these sonic properties?